Next, we are going to have Professor Henry Kai. So Henry actually graduated a few years ago from North Carolina State University with a PhD degree in statistics. She is currently an assistant professor in the Department of Statistics at the University of California, Irvine. So she's going to talk about some learning method in causal inference. And I'm going to ask her to introduce more about the topic. I just want to mention that she has done a lot of fantastic work in the field of causal inference, reinforcement learning, graphic models, and also their interchanges. So without further ado, Henry, the floor is yours.
Thank you, Lu, again for the great introduction and invitation. And it is my honor today to present one of my recent work at Pacific Causal Inference Conference. And today, I will talk about how causal inference can help natural language processing in terms of two property. One is heterogeneity and another is non-spuriousness. Okay, this work is joint work with my student, Wenbo, at the University of California, Irvine, and 3 collaborators from Acuvia, which is a consulting company in the industry. And they kindly share a very useful data set to motivate our work. And this work also accepted at this year's ICML conference. Okay, now let me start with a few motivation. So in the current era of causal revolution, as Guanbo and Cong mentioned previously, causal inference is a very hot topic, and there's a lot of usage that we can see, especially in genetics, economics, and etc. We all interested in identify the causal impact of an exposure on the outcome of interest, right? And existing work, most of them are focused on structured data. So what is structured data? For example, like so everything that already in the matrix form or some well-organized data is called structured, and in opposite to that is something called unstructured data. So for unstructured data, that includes raw text, image, and etc. However, from so far, there is much less work that we can see about how causal inference can be utilized for the unstructured data. And here is very useful review at I read about 1 year ago is causal inference in natural language processing made by Feder et al. At 2022. So this is a very good one that proposed a few challenging topic in the intercepting between causal inference and the natural language processing. Okay, so here is a motivation example that we selected from Acuvia about medical claim data to motivate how causal inference can be helpful in NLP. So if you can see the right-hand side, the left-hand side corresponding to the code, and each code corresponding to a particular medical and claim event. For example, you go to hospital, you see the doctor if you feel uncomfortable, and you pay something, and you make an appointment and buy some medication, and everything has been recorded as a code in the sequence. And the goal of this medical clinical data is trying to help us identify some key event in this sequence for each individual, so we are able to develop some early diagnosis and early treatment for those patients who may have some potential risk to the eye degeneration called GA disease for those patients. Okay, so as you can see, the key difference here is instead of finding some variable, we are finding a sentence or event from those unstructured data. And that's why it becomes a little beyond the traditional causal inference framework when we're trying to estimate the causal effects for a certain variable with structured data. Okay, so this type of question has been well studied in computer science literature. People called it rationalization starting from 2018. And rationalization is something related to the keywords rationale. And we are aimed to find the keywords in a paragraph or a sentence that can fully represent the full meaning. Specifically, a good rationalization should provide a similar prediction as the full text, what we call the task performance. And second, we would like to see that keywords can reflect the model's true reasoning process called faithfulness. And finally, we are able to use these keywords to explain to the wide audience. So that is called a plausibility. So all those three components consists of the trustworthy explanation for the full text, and that is the full definition of rationalization. As you can see, this can be understood as a variable selection in statistics, and the problem here is how we gonna select variable in terms of keywords. The good news is there is a bunch of methodology already developed in computer science called selective rationalization that can feed each different sentence with different lengths into a selector, and it will produce a sequence with important score, and hopefully we can identify the rationales with high scores, and those words with high score feed into predictor can help us fully discover the underlying true label. And this whole process is called selective rationalization. As you can see, basically we are extending the random variable selection in linear regression into variable selection in sentence using deep learning. And this type of methodology is still association-based approach, which has a lot of limitation associated with it. So to be more specific, why association-based method or why linear regression-based method or such kind of deep learning-based method has some problem. So here is a specific example to explain those kind of association. So it is well known in causal inference, correlation does not mean the causation. And this is an example about why correlation does not means causation. So this example is more like about 20 or 10 years ago from a Walmart market survey. People find when a young male go to supermarket who buy diapers will usually buy beer at the same time, or who buy beers will also buy diaper. So these two products will appear at the same time. So that's why Walmart usually put diaper and beer at the same place during that time frame. And people, after some investigation, people find all those young male actually are new fathers. They have to do babysitting while also drink beer to release their stress. So that's why these two products appear at a certain time. So you can see both beer and diaper are confounded by the same variable new father. And this introduced the spurious correlation among these variables. And these two indeed do not share any direct causation among them. So that's why this is called a spurious correlation. And such a problem become very severe in the natural language processing. So if you can see, this is another peer review data. So you can see Z1 and Z2 corresponding to some peer review sentence for the beer's aroma and the beer's taste. Usually aroma and taste are highly correlated with each other, but all of them are both confounded by the beer quality. And if we purely encode this whole sentence into the selector, the machine cannot tell Z1 and Z2 which is a true causes and which is a spurious one. So that's why handling the non-spurious becomes the most important, or one of the most important in natural language processing. And this kind of spuriousness is everywhere actually in unstructured data. So people also found it in the image data, in the video, where you can see the image classification of those animals are highly correlated with the background. So that's why the task of today is trying to use causal inference to help us filter out all those spurious variables and give us a true rationale for natural language processing. And to summarize, we have a few new desiderata for rationalization. So first of all, we would like to find all the efficient rationale for each individuals. And efficient means those causes are sufficient to explain the whole text information. And second, we also want those rationales to be non-spurious. So that is necessary causes for individuals that can that is not redundant at all to explain the text. So to solve this 2D data, we're gonna call some technique about 20 years ago from Julia Pro's Causal graph framework, graphical model framework. And one of the concept we're going to utilize today is called the probability of causation. So first of all, what is probability of causation? So that is a probability to measure the importance of one variable to the other. And we are still within the 2 random variable framework, and we're going to talk about extension to natural language processing shortly. So for the 2 random variable A and Y, we are interested in how A is important to the Y, and we build the causal graph like this and call the rest of the thing in the model as M. And all the confounder can be adjusted because we will do intervention directly on the variable of interest A. And now suppose we have A being true, Y being true. For example, we already include the beer's aroma into consider. We already see the beer's aroma to be nice, and we see the beer's review results to be nice, right? And we would like to say, what if we change the beer's aroma or change the sentence of it, and to see how reviews quality or reviews rate are gonna change for this type of instance. And the probability of it is called the probability of necessity. And using these 2 operators helping us create the counterfactual reality, will helping us to measure the importance of A towards the outcome Y of interest. Similarly, we can starting with A being false, Y being false. Say, for example, we have the aroma to be bad, and we say the quality review to be the score being low, and we force to change the aroma to be good one, and to say how the Y, the review quality, the score being good. And those kind of opposite way, we call the probability of sufficiency, and combining to become the probability of necessity and the sufficiency. So this can help us comprehensively measure the importance of the one single variable A towards the outcome Y. And now we're gonna extend those terminology concept to the unstructured data. Specifically, we're starting from a more tedious notations about the language. So we'll have X, which is input text with D tokens, and we have Z being the binary indicator to select those token or keywords into the data or not, and Y being the binary label for simplicity. And we can define the potential outcome as Y by setting capital Z as Z, so that is selecting certain words from the whole text. And then Y of capital ZI equals to small zi being the potential outcome when setting a specific keywords, while keep the rest of selection unchanged. So that is a framework for the text data. And then we're gonna build the structural causal model SCM for rationalization. As we can see, the whole text is the origin or the whole parents of the causal graph X, right? And then we use a selection to select the keywords or important part from the whole text, and using this to predict Y. And that's why the structural causal model starting from X, and then the selection is determined by the X, and the element-wise product Z between Z and X gonna determine the Y of interest. In this framework, we do not consider any unmeasured confounder, and we believe all the information already consisted in the data itself. So based on this structural causal model, we are able to extend the previous concept about probability of causation for rationales. Specifically, we are conditional on all the important information X, which is our original data information, and we will assume we do not do any intervention or we do not like change the arranged data at all. Well, we will use this selection Z, and we're starting with Z equals to Z and Y equals to Y, and to see what if we change the Z to be opposite, and how the Y gonna change as the probability of necessity. Similarly, we have the probability of sufficiency for rationales. Combining these two, we will have probability of necessity and sufficiency. So these three extend the previous two variable framework from Judea-Pro at 2000 for rationalizations. Okay, so far we established the probability of causation for rationales at a whole sentence level, and that is not good for us to do any variable selection. So that's why we further define the conditional probability of necessary and sufficiency for G's selection. To be specific, we only change or do the selection for the G's keywords for each sentence, and we keep the rest model as unchanged. And the difference of Y gonna become the importance to measure the importance of the D. And our definition beyond the existing word by extend the univariate binary level, and also we define this we extend this to more general settings, and by conditional on X, we allow us to directly select variables on specific keywords, and this type of estimation can be estimated from the observational data, and we'll talk about identification shortly. Now, before we talk about identification, once we use this CPNS, what is good for our variable selection? So here is a toy example. We only have three variables, x1, x2, and x3. Suppose the first two are the true rationales and the last one are spurious. And we will use a toy example to illustrate why CPNS is useful for us. Specifically, we down every possible combination of those keywords. And when we're looking at this graph, as you can see, any combination combine x1 and x2, which is the fourth column and the last column, will achieve the highest accuracy because they already capture the true causes, right? If we use this accuracy, we cannot directly select the true rationale. However, suppose we calculate the CPNS score, which is our probability of causation for each combination. As you can see, the middle one, x1 and x2, gonna yield the highest CPNS score. That's why it is very useful for us to do variable selection when the prediction accuracy cannot distinguish the spurious features from the data. So and with this motivation, we're gonna talk about what is the identification for CPNS. So follow the traditional literature in the causal inference, we also assume the consistent assumption, ignorability, and based on these two assumptions, we can establish the lower bound identification for CPNS score from the observational data, which is a maximum of 0 and the difference between two conditional probabilities. Okay, so based on this theorem, and we are good to go, we are able to adding the CPNS score into the rationalization framework, which we call the necessary and sufficient rationalizations. From this framework, as you can see, different from the traditional selective randomization, we have additional counterfactual rationales that are generated by flipping each single rationales from the selective model and calculate the probability of sufficiency and the necessity for each keyword to say which keywords is important for the predictor. And that's why we can help to filter out spurious variables. Okay, so based on this keyword, based on this framework, I'm gonna skip this detailed algorithm. And lastly, as you can see from our objective function, this L, Y hat is the loss function, and we're only adding the causality constraint into the model, so we are able to improve the variable selection in rationalizations to only find out the keywords without any spurious effect. Okay, so this is our main objective function and algorithm. Based on that, we apply our proposed method to the peer review data and the real data we mentioned at the beginning of the talk. Okay, for the peer review data, the good thing is we have token-level rationale from domain expert, which can help us to identify which is the true keywords from the data. And we apply the proposed method on the peer review data. And we find the proposed causal rationalization achieve the highest accuracy and F1 score in comparison to the existing natural language processing method. And that is still not enough. We done another synthetic experiment by inject some spurious variables that highly related with the outcome of interest, but not necessarily cause the outcome. And we find based on the proposed method, the false discovery rate FDR yields the lowest one, as you can see across all different scenario, while the competing methods all have the high rate of FDR, which means they are able to select the spurious rationales while our method cannot. Okay, so that is a good news. Finally, with all those evidence and technicians, we apply the proposed method to the real data analysis, GA data. As you can see, GA data has a much longer sentence as we see in the peer review data. The proposed method can achieve the highest AUC for evaluation. And we check all the sentence and event for case study. And we found the proposed method are pretty good to identify meaningful keywords such as type 1 diabetes, which already identified as the cause of eye degeneration, while the competing methods are hard to find any meaningful event related for the GA patient. So this is funding from our real data analysis. Finally, to conclude our message, there's still a long way to go to help natural language for processing from causal inference perspective, and two notable extensions that we may pay attention to, including the scalability, which may be one of the bottleneck for many causal inference methods, and another is incorporating time heterogeneity component from causal inference longitudinal studies, dynamic treatment regimen to help natural language processing to go further. So this is pretty much about my talk. Thank you so much for listening.
Thank you, Henry. Great talk.